Welcome to this lecture. This is a lecture series on entanglement theory, in support of SheQuantum, which is an organization supporting women in quantum information science who are doing research and learning about the topic from tutorials. This lecture series has been about entanglement theory. In the last lecture, we started talking about the Bell experiment, which is a very important experiment for entanglement theory. We talked about how deciding whether a state is separable or entangled is a computationally difficult problem. And then we talked about a criterion, a one-way criterion for deciding entanglement that's called the positive partial transpose criterion. Okay, and now we're going to move on to something called the resource theory of entanglement. It's an operational way of thinking about entanglement. So you might have questions like, given a state, how many teleportations can I do with the state? Given some number of maximum entangled states, how many of them do I need to prepare another quantum state? So that's the kind of question that entanglement theory addresses. Okay, so what is a resource theory? Here I've pointed to a nice review article on resource theories. Here's the link right here. And the idea of a resource theory is very general. What you do is you divide the set of all states into two sets. Some that you consider free, that you can use at no cost, and others that are not free, and we call them resourceful, okay? Resource theory of entanglement was really one of the first ones, if not the first, considered in quantum information theory by Bennett, DiVincenzo, Smolin, and Wooters in 1996. And the idea here is that entanglement is useful for information processing tasks like teleportation, dense coding, quantum key distribution. And so entangled states we consider to be the resourceful states. And separable states, in a sense, are not useful for teleportation. They're definitely not useful for quantum key distribution because there's that hidden variable, and an eavesdropper could possess that hidden variable. So that would be a big problem for doing secure communication. With the resource theory of entanglement, it's kind of simple to say what the free states and resourceful states are. The next question is, what are the free operations? And earlier on, we talked about local operations in classical communication. Those were the set of operations that can make separable states. So as it turns out, I'll just ruin the surprise. Those are the free operations in the resource theory of entanglement. Okay, so one argument to make why LOCC should be free is that communicating classical data these days is very cheap, right? Like we can blast classical information over the internet at very fast rates and at a very low cost. And so in some sense, you can consider it as free if you're trying to develop this resource theory of entanglement. So that's what we do. We just consider it to be free, classical communication. And then we also consider that any operation in Alice's laboratory is free and any operation in Bob's laboratory is free also. But what's not free would be like doing a C0 gate between Alice's lab and Bob's lab. That we would consider to be not free. Okay, so that's what local operations in classical communication are. To get a bit more specific, earlier we talked about quantum measurement channels, we talked about quantum instruments. So a one-way LOCC channel consists of Alice performing a quantum instrument. Remember, a quantum instrument has a quantum output and a classical output. So what she'll do is she'll send the classical output to Bob, and then condition on the classical outcome of that quantum instrument, Bob will perform a quantum channel. Okay? And an LOCC channel is just you build these up one after another. So you do a one-way LOCC from Alice to Bob, then you do a one-way LOCC from Bob to Alice, and you keep doing that. So you can do it an arbitrary number of times, but we demand that it's finite. They're not allowed an infinite number of one-way LOCCs. And that's what we call an LOCC channel. Okay, and one thing you can show is that an LOCC channel can be written as what's called a separable channel. And this is kind of like the channel generalization of a separable states. Okay, so the EZ and the FZ, those are sets of completely positive trace non-increasing maps, such that the overall map, when you take the sum of these, that is a quantum channel. Okay, so every LOCC channel you can write as a separable channel, but the converse statement is not true. There do exist separable channels that you cannot write in terms of LOCC. And it's a bit complicated to get into that, so we're going to skip that, but there's a reference here if you're curious. Okay, so here's a depiction of LOCC. This is a figure that's in the book I mentioned that I co-authored with Sumit Khatri. It's a figure that he designed. And it's a depiction of LOCC. So I believe you can find this in the chapter on quantum mechanics, which gets into all kinds of channels. So as we said, LOCC consists of Alice doing a quantum instrument. There's a quantum output. She sends the classical output to Bob. Bob then does a channel conditioned on the value X1 sent by Alice. Then the next round is the opposite. Bob does the measurement, sends the outcome to Alice, who then does a channel conditioned on the outcome, etc. So that can continue for some arbitrarily large but finite number of rounds. One thing you can show is that LOCC channels preserve the set of separable states. So what does that mean? Suppose that sigma is separable, L is an LOCC channel. If sigma is separable, we can write it like this. If L is an LOCC channel, we can write it like this. Then just using linearity, we can bring the sum outside, the P lambda outside. And then when you look at this state here, it's sort of manifestly separable, right? You can see that it's a convex combination of product states. So the point is that by LOCC alone, you cannot create entanglement when you act on separable states. You stay within the set of separable states. So that's a good reason to consider LOCC to be free channels in this resource theory, because they preserve the set of free states. That's exactly what we're saying here. Okay, so now we're getting into entanglement theory in a bit more depth. This is what we call the axiomatic approach. And we just say that a function E is an entanglement measure if it does not increase under LOCC, right? So more formally, E is an entanglement measure if this inequality holds for every input state and every LOCC channel that realizes the state omega, right? So all it's saying is that E is an entanglement measure if it does not increase under the action of LOCC, which is the first statement written. Okay, and that's a pretty important concept for entanglement theory if we're interested in quantifying entanglement. Why would we be interested in quantifying entanglement? Well, we'd want to have a sense of, like, if we have rho, how many teleportations can we do with the state rho, right? Or how much does it cost in terms of EBITs to prepare rho by means of LOCC? So those are operational tasks that we'll talk about later on. So we have this basic axiom. What is a simple consequence? A simple consequence is that this entanglement measure is minimal and equal to a constant on the set of separable states. Why is that? You can get from one separable state to another by means of LOCC. So if you think about it a bit, it means that the entanglement measure just has to be the same for all separable states. And it's equal to a constant. And so it's conventional just to set this constant equal to 0, to say that, well, for separable states, there's 0 entanglement. You know, a separable state is free, so its value is equal to 0. And well, we can also, you know, we said that the entanglement measure is minimal on the set of separable states. So if we set this constant c equal to 0, what it means is that an entanglement measure is non-negative for every state. And it's equal to 0 if the state is separable. What are other desirable properties? You might want more than we just said. You might want the 0 value for the entanglement measure to be if and only if, right? So the entanglement measure is equal to 0 if and only if the state is separable. That would be stronger than the one-way implication we had here. Another nice one is that the measure is invariant under classical communication. So what are we saying here? There's a state that we call a classical quantum state. So it's classical on X, and then it's quantum on A and B. And so what we're saying here is that suppose that Alice possesses the classical system, and we're computing the entanglement between A, X, and B. If Alice were then to communicate the classical system to Bob, and we'd compute the entanglement of A and BX, that should be the same value. There should be no difference. And then furthermore, that should just be the weighted sum of the individual entanglements of this state. So that's a nice property to have, and many interesting entanglement measures do have that property. Other desirable properties include convexity. So suppose that some state is a weighted mixture of states. Then the idea is that the convex combination of entanglement values should not be smaller than the entanglement of the average state. So the way that you can think about this is if this property holds, then it's like entanglement does not increase under the discarding of the classical system. So that's a way to think about convexity. Because if you were to discard the classical system, you would get the state rho x, you know, the mixture of the rho x's weighted by px. Okay. Another desirable property is called additivity. So if you have this kind of tensor product where Alice's system splits into an A1 and A2, and Bob's system splits into a B1 and B2, and they have this tensor product of states across the system, then it's kind of a nice property if the entanglement is additive, right? So the entanglement between all of Alice's systems and all of Bob's systems is the sum of these individual entanglements. And that's for the tensor product structure. Okay, we're starting to run out of time, but I think we can do this. Why don't we try to do this and then we'll stop. So there's something called selective LOCC monotonicity. So we talked about LOCC monotonicity as like the defining property of an entanglement measure, but there's a refined version of that, which is often useful. And it's a bit more complicated. Let's suppose that this is a collection of maps such that the sum of them is an LOCC channel, okay? And suppose that each map can be written in this like separable form, okay? But again, we demand that the overall map is an LOCC channel, okay? So selective LOCC monotonicity is saying that let's take each of these maps and act on an initial state with them. And this will be the probability of like getting a certain outcome from a measurement, okay? And the post-measurement state will be this omega x. So what this procedure does is it transforms the original state to this ensemble where you have the state omega x with probability px. Okay. And it satisfies the selective LOCC monotonicity if this inequality holds. And what it's saying is that entanglement does not increase on average, right? So there's some initial entanglement for this initial state. And then for each of these final states after this procedure, there's some amount of entanglement. And this is the average of those entanglements. So this is saying that selective LOCC monotonicity entanglement does not increase on average. How do you prove that? Well, there's a way to do so, and Sumit and I get into this in our book. The book's called Principles of Quantum Communication Theory, a Modern Approach. So suppose that E is a function that has these properties. One, invariant under classical communication. That's what we talked about over here, right? So suppose you have that property. And suppose that it's also obeying data processing under local channels. So you have some initial state, you do a local channel on Alice's system, you do a local channel on Bob's system to get this output state. And suppose it does not increase under the action of this local channel. Then you can conclude that E is in fact convex and a selective LOCC monotone. So many interesting entanglement measures have this property. Later on, we'll talk about a few of them, entanglement of formation, relative entropy of entanglement, squash entanglement. They all obey this. They have the convexity and selective LOCC monotonicity. All right, let's stop there and we'll pick up again next time.